Okay, welcome to extreme values of functions. In this section, we're going to look at the relationship between the graph of a function and its derivative. Way back when, before calculators, the way we were able to graph a function was by using the derivatives. So now that calculators are here, you don't really need this as much. However, you have to remember that on the AP exam, you will be asked to do these things without a calculator. So our objective today is to determine what a critical number is, determine the extrema, and in the second video, we're going to look at the mean value theorem and Rolle's theorem. So again, as I've said before, calculators in the past, before we had calculators, we would use calculus to graph functions. But even though we have calculators now, the AP exam is going to be partly calculator inactive, mostly calculator inactive, and you will need to be able to use these skills to graph functions. Let's talk a little bit about what absolute extreme values are. They're either a min or a maximum. Now this is not in your notes, so just kind of pay attention to this without taking notes for a second. Sometimes they're called global extrema. So you need to look for both terms, absolute extrema and global extrema. Okay, so if we were to look at this parabola, and if its domain is negative infinity to infinity, we would notice that there is only one absolute minimum. And that absolute minimum occurs at 0, 0. Also notice that there is not an absolute maximum. Because both ends go to infinity, there is not an absolute maximum on this function. There's only an absolute minimum, and that absolute minimum occurs here. Now, if we restrict the domain, notice that this is a closed interval on both sides. When I restrict this domain, notice I now have an absolute minimum here and an absolute max here, because the domain is restricted and we're not going to infinity anymore. In this particular case, this is not a closed interval because we have a parenthesis on the 0, which means 0 is not actually included. And because 0 is not included, there is not an absolute minimum. However, there is an absolute maximum. There's still an absolute max. Again, this is an open interval on 0, 2. Neither 0 or 2 are included, so therefore there is no absolute min and no absolute max. Now, this is in your notes, the extreme value theorem, and generally there will be one question on the AP exam that will require you to know the extreme value theorem. And it basically says if a function is continuous, then there must be a max and a min. There must be a max and a min if a function is continuous. And on a closed interval. I'm sorry, it's continuous and on a closed interval. If both of those conditions are met, then there has to be a maximum and there has to be a minimum. In this particular case, the maximums occur at what we call interior points. We would say here and here we call these interior points. So we have an absolute max and an absolute min. On this case, even though there's not an absolute max or an absolute min, there's not a max or a min, because it's on a closed interval, the absolute max and the absolute min will be on the endpoints. This has a maximum at an interior point, but the minimum is the endpoint. So this is our minimum, our absolute minimum, and this is our absolute max. Now, sometimes we have what we call a local max or a local min. A local min is just a point on the curve where it goes from, where their derivatives go from positive to negative, or negative to positive. So these are what we would call, this is an absolute min. This is what we would call a local max. That's a local min. That's an absolute max, but it's also a local max. Now, some books would refer to this as a relative min. However, I think most textbooks do not consider this in relative min because it's an endpoint. And endpoints can only be absolutes. Here's an important point. Notice here that the derivative at these points are either 0 or undefined. For these 2 points, the derivative is 0. At this point, the derivative is undefined. And this is an important concept to note. Which brings us to this next thought. If a function has a local max or a local min, then the derivative is either 0 or it does not exist. If it has a local max or a local min, the derivative at that point will either be 0 or does not exist. And we call the points when the derivative is 0 or does not exist, we call that a critical point. Critical points are not always max or mins. Okay, so you need to know that. Just because it's a critical point does not make it a max or min. The other thing that you need to know is that in order for it to be a critical point, it must be in the domain of the original function. I think in your notes it says a special note about critical points. And that is, critical points must be in the domain of the original function. Okay, how to find max and mins analytically. The first thing you want to do is you want to find the derivative of the function and see where the derivative is 0 or undefined. This is the critical point. Then you want to find the value of the function at each critical point. And then you want to do a sign chart to see if the slope changed from positive to negative or negative to positive. And if it's on a closed interval, you have to check the endpoints. Number 4 is very important, so please check that. If it's on a closed interval, you have to check the endpoint. Okay, once again, critical points are not always extrema. We see in this case the derivative is 0 at 0. However, that is not a max or min. Again, the derivative is undefined at 0, but that is neither a max or a min, not an extrema. Okay, so let's do some examples. We're going to find the critical numbers of the function. So we start by finding the derivative. And to find the derivative, I use the quotient rule. Now, once I have the derivative, my next step is to set the derivative equal to 0. I have to see where the derivative is 0 or where it's undefined. So because we have x squared plus 1 equals 0, that will never be 0. And so now we also have to see where it's undefined, which is where the denominator is 0. And we see that happens at plus or minus 1. However, plus or minus 1 is not in the domain of the original function, so this actually has no critical numbers. So if we were to graph this, we would see that it does not have it doesn't have an absolute max or an absolute min. It doesn't have a local max or a local min either. Okay, I think this is different from your notes, so you want to change your notes to reflect this problem. Okay, so the first thing we want to do is find the derivative. Again, we're going to use quotient rule. Then we're going to simplify the derivative and set the numerator equal to 0 to find the critical numbers. And then we set the denominator equal to 0. Now, once again, you want to notice that t equals 2 is not in the original domain. So we found our critical numbers were 0, 2, which is not in the domain, and then we have to check 3 and 5 because they're endpoints. and then 4 was our other critical number. So 0 is outside of our interval. Our interval is from 3 to 5, so that's outside of our interval. 2 is outside of the interval, but it's also outside of the domain. So we just have to look at 3, 4, and 5. So what I've done is I've taken those values, 3, 4, and 5, and I've inserted them or substituted them back into the original equation to find the value of the function there. And from this, I can see that I have an absolute maximum when t is equal to 3, and that absolute maximum, the value of that absolute max is 9. I have an absolute min when t is equal to 4, and the value of that absolute min is 8. So you have to be careful how the question is asked on the test. If I ask you when does the critical point occur, when does the absolute max occur, you would say at t equals 3. If I were to ask you what is the absolute max, you would say 9. Okay? So again, we have a closed interval. So the first thing we do is find the derivative. Then we set the derivative equal to 0. And again, we make our table looking at our critical numbers and our endpoints. Once again, -2 is outside of the interval, so I don't have to worry about that one. And then I have to evaluate 0, 2, and 4. So I have a local min when x is 2, and that local min is -16. I have an absolute min at x equals 2, and that absolute min is -16. I have an absolute max at x equals 4, and that absolute max is 16. Okay, so I would suggest that you pause this and you try this one on your own, and then come back and see the answer. Okay? All right, once again, pause the video and you try it. Okay, one last one. Again, I would suggest that you pause it and you try it and come back and see the answer. Now, for this example, we're finding a local extrema on an open interval. Now, because the interval is open, we do not have to test the endpoints, and we will use other methods later to determine whether or not it's absolute. So the only thing that we're testing now to see if this is a local extrema. We do this the same way. We're going to start by finding the derivative and seeing where the derivative is either 0 or undefined. So we find our critical numbers are 0, -1, and 1. So what we're going to do is we're going to use what we call a sign chart. We're going to take a number less than -1, and we're going to plug that into the derivative. So we're going to evaluate the derivative, well, let's say -2. I don't care about the actual value of this, I just want to know if it's negative or positive. So I'm going to take -2, substitute it into the derivative, and I get a negative answer. I'm going to do the same thing with something like -1.5. I'm sorry, -0.5. And I am going to evaluate that into the derivative, and I see I get a positive number. And then I'm going to take a number between 0 and 1.5, and once again I'm going to substitute that into the derivative, and I get a negative number. Then I take a number greater than 1, let's say 2, and I'm going to substitute that into the derivative, and I get a positive number. Now from this I can determine if it's a local max or a min. Now there is this is actually the first derivative test. But because I don't like to memorize, this is the way I will have students do this. So if my derivatives, let me get a pen right quick. Someone let me get a pen. Because my derivative, okay, that didn't work. When my derivative is negative, that means that my function, the original function, was decreasing. So when my derivative is negative, that means that my original function looks sort of like this. It was negative. It was coming down. And again, I need a pen, sorry. Okay, I'm not sure why that's not working. Okay, sorry. It's not working, but it would come down. You'd have a negative, and then it goes positive. So you can see it sort of looks like a V. You have a negative value, and then it goes positive. So you can see that that is going to make a minimum. Then you have a positive, and then it goes negative, and you can see that that's going to make a maximum. And then you have a negative, and then your slopes go positive. You can see that that's going to make a minimum as well. So we can determine that at -1, there's a local min. And at 0, there was a local max. And at 1, again, there was a local min. And I wish this was working so I could give you a better visual of that, but it's not. And it's just going to irritate me because I can't get it to work. What if I try the highlighter? Yeah, no, nothing. Sorry. Okay. All righty. I'm just going to move on. Okay. So once again, we're going to do the exact same thing. We're going to find the derivative. We're going to set the derivative equal to 0, or when it's undefined as well. And then we're going to find our critical numbers. And again, we're going to take a sign chart, and we're putting those numbers back into the derivative. Okay, so we notice that from negative to positive, it remained negative. So that tells me that 0 is neither a local max nor local min. But it changed from 4, it went from negative to positive. And because it went from a negative slope to a positive slope, then that indicates it's a local min. And how I'm getting the fact that it's a local min at -19.33 is by substituting it back into the original function. Okay, so once again, we're going to do the same thing. And remember here to use product rule. You're going to use product rule and chain rule. Set our derivative equal to 0. Find our critical numbers. Remember, e to the x or e to the negative x is never 0. So the only place it's going to be 0 is x equals 1. I take values to the left. I take values to the right. And because my slope went from positive to negative, that is a local max. And the local max is 1 over e. And I got that by substituting 1 into the original function. Okay, I would suggest that you try those two, and we can go over those when I see you. Okay, so here's what you need to know. You need to know that critical numbers occur when the derivative is 0 or undefined. That if it's a local max and mins will always occur at a critical point. However, all critical points are not max or mins. To find the absolute max and min, remember to check your endpoints. I would suggest that you finish the 2 problems in your notes and then do 17 through 25 in section 3.1. All right, have a great day, and I will we'll have the next video in a minute.